Morning, everyone. So we're going to continue on with our study in momentum. We did talk about impulse as a new concept yesterday, looking at a change in momentum. Impulse is something that you can apply by acting a force on for a certain amount of time, for a collision time. We're going to start off just practicing a one-dimensional sort of momentum impulse question, just reviewing a little bit of kinematics. And then what we're going to do over the next two lessons is actually look at two-dimensional cases of this. Basically, again, momentum is a vector, so unfortunately with two dimensions, you need to break up any components into x and y. We still have our main physics, which says momentum should be conserved. We'll do an impulse case and vector addition case, so basically the two-dimensional equivalent of things that we've been doing so far. So just before we get to our first two-dimensional problem, this is just a standard momentum kind of impulse question, just in one dimension. So let's see how we do with this one here. The two dimensions does get a little more complicated because of those components, but if you're familiar with what it is in one dimension, it shouldn't be that hard to extend it to the 2D case. So we'll start off here. Let's imagine we have a diver. So we have our diver. I'm going to give you the mass of this diver here. Say he's the average 50 kilogram mass. The diving board that he's standing on so far is going to be 15 meters off the water. So let's imagine this is water or the ocean or swimming pool or some sort. We're going to imagine this time for the diver, he just starts off at rest. He just takes a step off this board here, and all he's going to do is he's going to drop straight down. Okay, so he's not going to cannonball, he's not going to actually run forwards or anything. He's just going to step over the ledge and then fall downwards and then hit the pool. First question here. Do this in sort of part A, B, C here. Part A is to calculate here find the final velocity upon hitting the water. So that one there is just a standard kinematic problem here. You know acceleration due to gravity and all that. You should be able to find the velocity, the speed he has in hitting the water. As you may have some intuitive understanding with this, when this person hits the water sort of acts like a friction. The water sort of slows this person down. Our bodies are buoyant, so it can actually support our weight. We're not just going to infinitely sink downwards. We're going to eventually come to a stop. So at this point here, the instant that he hits the water, he's going to be traveling at some really, really fast speed. He's going to end up a little bit lower, and by that point there, he would have come to a rest again. Okay. So this part here is part B of the motion. During he hits the water to when he comes to a stop, I want you to calculate the impulse on the person from the ocean in stopping him. Okay, so I want to calculate what is the tendency to change momentum. The tendency was to fall when I hit the ocean, but by the time I actually come to a stop, all that momentum is now gone. We did see in yesterday's lesson momentum is conserved, so if I did also measure how much the water's momentum changes by as well, it's exactly equal and opposite. But so far we're back to just studying just the one person by itself. So the impulse on the person in stopping his velocity. Part C of this, we're going to use one of the formulas for impulse to actually calculate if the ocean supplies an average, I'm just going to make up a number here, 1,000 Newton force, find the collision time. So I know even afterwards he's going to end up still in the water. He's going to just be swimming there. But basically, it's finding the time where the water is actively supplying the 100 newtons to actually bring him to a stop. Eventually, when you're at a rest, he's just floating there. The water doesn't need to push up on him anymore. So find that collision time or the contact time. Notice that that time there will be different from the time it takes to fall. That part there we dealt with in part A. And then what I want to do here is I want you to calculate how deep does the diver drop? So I want to know this distance here, basically how far until he comes to a stop before he needs to start treading water and start swimming upwards. So you can pause at that point and then you can see how you do. There is, if you've noticed here, a lot of kinematics in this question here. So we see a lot of the concepts from chapter 1 come back again and again. So make sure you're comfortable doing those kinematic equations. It's going to be useful in today's lesson as well. But let's just do these things here part by part. In part A here, it's a pretty standard kinematic question. We know the initial velocity here is actually at a rest. We're going to call the final velocity in part A. Blindfold on was when the swimmer was on the top. The blindfold off was when he hit the water below. So I'm going to use the formula here. Since I have distance, since I know it's gravity that's accelerating him, we can use Vf squared equals Vi squared plus 2AD. Should be fairly easy to find the impact velocity, the velocity he actually hits the water with. So I don't know what his final speed is at the end, but I do know initially he's at rest, so 0, plus twice. I'm going to use the negative 9.8 because I'm going to use negative for the downwards direction. For the displacement, it also needs to be negative 15. He started out way up here, and now he's 15 lower than where he started. So I need that extra negative 15. That part there means down, as does this part here mean down. In that case there, let's just solve through the math. We have Vf squared is equal to 2 times 9.8 times it by 15. This is going to equal to 294. When you square root a number, you can get the positive root or the negative root. In this case here, I know the velocity is downwards, so I'm actually going to take the negative answer. So square root of 294 gives me roughly about 17 meters per second, 17.1, just rounded there, 17. So we calculated that one here pretty easily. It's just a kinematic question. Didn't really need momentum. In this case, you're looking at the problem. This tendency to stay in motion, he's a 50 kilogram object, and his speed is actually 17. He has a tendency to fall. Were it not for the water, he would continue accelerating, he would continue speeding up, his impulse would continuously change. But what happens in part B here is he actually strikes the water. And like we mentioned, water actually supports him, water actually slows him down, water actually supplies the impulse to get rid of this motion. He's going to eventually bring this diver here back to rest. So in this case here, let's think of our formulas. So far we have impulse or change of momentum. I could have done P final minus P initial. I could actually calculate if I do know the masses of everything. I know the mass of the guy here. I can do m times v, no problem. A slight iteration of that was m v final minus v initial. That's the one I'm going to use this time because it already quotes from a velocity. I already knew the velocity in part A. I can calculate the impulse just looking at a change in velocity. Remember, it's just a scaled up version of mass. And then we had the last formula. I'm going to reserve that for part C. Part C here actually talks about force. So I would probably use, this is Newton's second law worded in momentum. I'd probably use that formulation. Remember, once you calculate what the impulse magnitude is, you're more than welcome to use the impulse as a number for other formulas. So let's just try this out here, focusing mainly in part B. He's already hit the water. So in this case here, we're going to say to find the impulse that the ocean tries to stop him, it's going to try to remove the mass of the person and try to go v final minus v initial. So the guy itself was 50 kilograms, like we said. The v final this time, notice I'm doing a different initial, different final. This time for part B, initial is actually the moment that you hit the water. This time it's actually a starting speed that is actually negative 17. Right? Earlier, the initial was up here because I was just dealing with this first part of the motion, that falling time. But in this case here, we're resetting initial. He's already hit the water. And now I'm resetting final to be when he finally comes to a stop again. In the end, he's going to come to a stop, so it's going to be 0. Again, it's a scaled up form of change in velocity. Basically 50 times 17. This gives me 850. Make sure you have units. So mass is in kilograms and velocity is in meter per second. You'll notice that this impulse is in the positive direction. That positive direction implies that this is upwards. For us to actually change his momentum, at first he was just dropping, he would just fall endlessly into the ocean. The ocean actually needs to supply an impulse, has to get rid of 850 kilogram meter per second, has to actually push upwards to actually support this guy to eventually bring him to a stop. So there we go, that's the impulse. You could hypothetically, I just wanted to give you a nice little parallel here. This is how I would do it because we're looking at impulse, we're looking at force and whatnot. You could have hypothetically actually done this with forces. I actually want to just give you the parallel of it. Sometimes you have enough information to do it the kinematic way, the forces way. They should end up giving you the same number. Sometimes you're not given enough information. You only can do it one way or the other. In this case here, we can actually do it both ways. So what I mean by this part B here, I could actually transitioning to part C, looking at the 1,000 Newton force, the impulse way is fairly easy. If you want to find the collision time, the impulse by definition is force times time. I can just rearrange that for the time here. Time is the impulse divided by force. I know I need to supply an upwards change your momentum by going positive 850 kilogram meter per second. If I'm told on average the force is going to be 1,000 newtons, that was given to us in the question, I divide it through. Again, the amount of contact time is fairly small. Just like if you took a shot with a hockey stick, the amount of time that the water actually acts is actually really minimal. Notice that this time here is not the time he took to fall. In falling 15 meters, it probably took 1 second, 2 seconds or so. It's not this 0.85. Also, after this 0.85, the guy would still be swimming in the water. The clock would continue run. I'm not considering the time he's actually just swimming around. I'm actually considering just that 8.5 seconds where the water supplies an average of 1,000 newtons just to bring you to a stop. So this is specifically the time for part B, starting when he hits the water, final when he's already at rest, not any time afterwards. Because we know the force, we could have actually done some of our dynamics kinematics stuff from earlier. We could have said something like F net is equal to ma, right? There's an unbalanced force. If the water is pushing up on him, a positive 1,000, given that he's a 50 kilogram mass, I could find what the corresponding acceleration is. 1,000 divided by 50. It's actually an acceleration of 20 meter per second squared. That may seem like quite a lot, right? Every second you're 20 meters per second faster. That's like speeding up by 60 kilometers per hour, 70 kilometers per hour after every second. But remember, this acceleration is only applied for a very split second. It's only applied for a very short time just to bring him to a stop, hopefully not with a really hard hit. Once we know the acceleration, we could actually do this using kinematics. So for example, if I wanted to verify this collision time, I could have said Vf is equal to V naught plus At, right? Remember, our initial was when he hit the water, so he was going downwards, negative 17. His acceleration, this time we're not going to use gravity. Because of water sort of counterbalances gravity, we're actually going to use the acceleration. This 20, it's what's being used to stop him. That 20 is in the upward direction. We're interested in finding the collision time, but we know the water eventually brings him to a stop. If you do that math there, you're going to get 17 is equal to 20t, just showing you a parallel way of actually solving this problem here. 17 divided by 20, give or take, it's 0.85 seconds. So the amount of time it takes for the water to accelerate you at 20, for the split second of 0.85, that's enough to get rid of all your momentum and bring you to a stop. So that's sort of the more kinematic way of doing it. Lastly here, we need to find how deep does the diver dive. So this part here looks like a kinematic question. Once you have terms like A and T, it doesn't get all that hard. We've already practiced the formula, let's say Vf squared, Vi squared. We practiced this Vf, Vi plus At. Just as practice here for part D here, maybe I would do D is V naught T plus 1/2 At squared. Remember, all three formulas are sort of interrelated here. To find the distance that he ends up falling in, his initial velocity and going sort of through the water here is, initially he was going at 7. Let's even use the directions here. He was falling into the water at negative 17. The contact time he travels is going to be 0.85 before he comes to a stop, plus a 1/2. The acceleration, we're tempted to say 9.8. The 9.8 was true for this top part of the motion because he was just falling because of gravity. Remember, the acceleration when he hits the water is more so due to the net force from the water. So I'm actually going to use 20. That's in the upward direction, so positive 20. 1/2 A t squared, again 0.85 squared. Again, the more you know, like A and T, the more options you have with the formulas. So let's just punch our way through here. 17 times 0.85. This gives me a negative 14.45. Let's add the 0.5 times 20 times 0.85 squared. Give or take a little bit of rounding. It's always best if you can keep all your numbers through. I'm going to go minus 14.45 plus 7.225. I'm getting a distance of dropping negative 7.2 meters. I'm going to be below 7.2 meters upon hitting the water. Okay. So hopefully that's a nice, just a summary kind of question. That one there is still a one-dimensional problem. It looks at sort of momentum. The only formula I didn't really practice with you here is actually just a plain old m times v. But you see concept of impulse, and you even see a shout out to dynamics for Newton's second law, and also some kinematic stuff. So just want to show you that all these chapters, they end up working together. Okay. So without further ado, we're going to start transitioning our way into 2 dimensions. If you understood this physics here, basically everything is the same. The only thing that's different now is because of the 2 dimensions, like I mentioned, we're going to need to do components. We're going to break up any annoying diagonals. Diagonals are really hard to compare with each other. Let's use sine and cosine. Let's create some right triangles, and then let's figure out the component parts of it. So this one here, it is going to start into our two-dimensional momentum section. There's a couple ways of setting this up. So today I just want to introduce to you one way. Okay. The first style of problem I'm going to do with you for today is going to be called a conservation question. We had seen a conservation problem when we had our rocket example from last week. It started off having some mass, some velocity. It broke into two parts. Momentum had to be conserved. We said P in has to equal to P out. The physics for all this 2D momentum stuff, whether it's a conservation problem or the problems we do upcoming, the physics is all going to be the same. P in has to equal to P out. But the only problem is because now we're going to be in two dimensions, we're going to need to deal with the horizontals separately. In the x column, we're going to need P in equals P out. And as well, in the y column, we're going to need a P in equals P out. So it might be helpful to separate those two columns so that way you don't accidentally confuse values jumping across the columns. Or the other way you can do it is you can just say Px in equals Px out, Py in equals Py out. Notice that it's the very same physics. It's conservation of momentum. Momentum cannot be created or destroyed in a collision or in a conservation in a bomb style question here, but because of the two dimensions, we need to deal with it separately. Okay. So for this conservation problem here, let's just jump straight into a question. We'll do this as a bomb problem. Okay. So imagine there's a bomb that's just sitting there. Let's imagine for a second that this is a top view of the question. So you're in a helicopter and you're looking downwards on a bomb that's just sitting there. We're going to start off with the before picture, right? So we're in the helicopter. Let's say this bomb here is 10 kilograms to start off with. This is the before. It's not doing anything, it's at rest. And as the name suggests, it's a bomb, so it's going to explode. This one here could end up exploding into many millions of fragments here. Just for simplicity, I'm going to break it up into 3 fragments. So looking down here for the after picture, we had the bomb initially sitting right there. I'm going to give you some numbers. Let's say the top part of the bomb is 2 kilograms. It ends up going just pure northward direction. It's going to go 5.0 meter per second true north. Okay, so I'm keeping the directions fairly simple to start, so we're not going to deal with it too hard for components. I'm going to take this piece on the side here. Let's say it's 2.5 kilograms, and let's say it travels off. It's a totally different piece, so it can travel off at a totally different speed. So let's say 4.2 meter per second, that's eastward. Because I have a picture, I don't need to worry about positives and negatives. My question is going to be, seeing as we're 3 fragments, what is the mass of this third fragment? I can call it M3 if you like. And what's the velocity? Intuitively, our brains already do this. Based on a conservation of momentum, if we had pieces flying off up and flying off downwards, we would imagine this mass here ends up going this way. And what we're actually saying in that situation, just big idea here, we're saying that this mass here, because my piece number 2 is flying off east, something has to fly off west to conserve its momentum. Because something is flying off north, this piece here also needs to fly off somewhere south to kind of cancel out momentum to make sure momentum is actually conserved. So our brains naturally do this. We have good intuitive experience of this. We just need to be able to calculate through with some math. So that's the setup as is. I kept the question fairly simple because the P in, because we're at rest, if I try to do a M1 times V1, I don't care that you're a mass of 10 because I'm not moving. I have 0 total momentum. So it doesn't matter if we're X or we're in Y, the total momentum at the start is actually 0. So let's just do this one by one here. Let's deal with the X first. Okay, instead of separating the 2 columns like X and then Y kind of side by side like that, I'm just going to deal with X. And then after we're done calculating through X, we're going to deal with Y as a totally separate row. So in X, I'm going to take, what's the Px of the initial bomb? This has to equal to 3 pieces. For every piece, I should have a momentum. This should equal to P1 plus P2 plus P3. Again, we're doing 2 dimensions here. I'm just going to call this P1x, P2x, and P3x. Just the horizontal part of it. Okay. So momentum conservation, the physics, believe it or not, is just this easy middle part. It just says it has to be equal. It has to be conserved. It has to stay the same, left side and right side. We already said initially, because we're at rest, this has no tendency to stay in motion, and m times v would give you 0 horizontal momentum. There's no momentum going left or right. Later on, I could give you, let's say this were a rocket, it could actually be moving. That would actually change this number. But the physics, the math that we do from here on out is just going to be the same. So let's look at each of our pieces here. Let's call this piece the 2 kilogram piece number 1. It's a 2 kilogram object. We want to say something like m1 v1x plus m2 v2x plus m3 v3x. That's because we knew momentum is the motion product between m times v. But what we're going to see here is because we're focusing on just the x direction, my first piece is actually only going northward. How far is this going left or right? It's actually 0. So in this case here, when I just sort of crunch our way through the numbers, I have a 0. My first piece, which is a 2 kilogram mass here, I want the horizontal part. Well, it's not going left or right. Horizontally, it's only going 0. I'm not going to put the 5 until we deal with the y side. Let's do the same for the second piece here. Second piece is our 2.5 kilogram mass. That's the one on the right-hand side here. 2.5 kilogram, this one here is actually going pure east. Our east convention here is positive, so I'm going to multiply that by 4.2. That does take away with it some momentum. And then for momentum to be conserved, my last piece, hopefully you're able to find for me how big this mass is. Right. You see that initially we were 10 kilograms. If 2 kilograms travels out this way, 2.5, 10 minus 2 minus 2.5 gives you, I think it's 5.5, double check my math. So conservation of mass actually came into play there, shouldn't be that bad. So we know that the mass here at the very least is 5.5 kilograms, and we know it's going to have some Vx to go off. So we're saying for starters, there was no momentum for the bomb. This piece here was going pure north. It has no added momentum. It doesn't take away any horizontal bit. This part here takes away some horizontal positive momentum. What speed does the third object have to cancel out this momentum so that we're still 0? So let's try it out here. We have 0 is equal to 0 plus 2.5 times 4.2. This gives me here 10.5 plus 5.5 v3x, okay, piece 3. I'm going to subtract the 10.5 over. I get 10.5, negative 10.5 has to be 5.5 v3x. And therefore, v3x, the horizontal part of this third piece, is 10.5 divided by 5.5. That gives me, give or take, 1.9 meter per second. So that goes with our intuitive understanding. If I had one piece that was supposed to go, in this case here I showed you this blue piece here goes to the right, for us to make sure momentum is conserved, at least this third piece here has to go something to the left to counteract the momentum. Careful, it is momentum that gets conserved, not velocity. As we get into the details more in the next 2 days or so, sometimes people are going to go, oh, you went 4.2 to the right, the other piece has to go 4.2 to the left. We're not saying speed has to equal. We're saying the total momentum, the motion product, once you multiply the mass times velocity, 2.5 times 4.2 gave you 10.5. Yes, it's 10.5 that has to go to the left, but being a totally different mass, for me to add the same 10.5, my speed only actually has to be negative 1.9. So careful, the physics says conservation of momentum, not conservation of velocity. Okay? That's just one dimension so far. The other dimension we're going to do very similarly. We're going to track all the verticals, all the ups and downs. So in this case here, we started off with no momentum. This was not going left or right. So we're going to take the py in, which is also going to be 0. It's also separated into 3 pieces, p1y plus p2y plus p3y. Sometimes problems will just give you the momentum, so we'll just leave it as p in this question because we are given masses and velocities and we're interested in how fast that last piece goes. It's good to just write right away, oh, we can have a m total v total, I can have a m1 v1 final, m2 v2 final, m3 v3 final, because we know momentum is m times v. We already said, I don't care that this mass here is 10 kilograms, it wasn't moving to begin with, it's not flying north or south at the beginning, so it has 0 momentum. The first object here, let me just double check my numbers, it was a 2 kilogram mass, but it was traveling at 5 meters per second. This is purely in the north direction, so definitely a 2 kilogram traveling at 5 has a tendency going upwards, 10. The other one I left fairly easy because this is going a pure eastward direction. There is no up or down component from that part. So in that case there, we're going to just add 2.5 as our mass, but it's not going left or right, so it's 0 from there. We're going to get the last piece here. What does the 5.5 have to travel at? In this case here is v3y, the velocity in the vertical direction, so that I know initially the first piece had 10, so that this v3y can cancel out the 10. Again, the piece number 3 is actually a little bit bigger mass. What velocity does it need to cancel out that 10? So let's just work through some of the math here. 0 is our total momentum. We need to get rid of 10. The second piece gave you no vertical momentum, so that's 0. That has to equal to 5.5 v3y. 5.5 v3y has to equal to negative 10. And all we're going to do is divide the 5.5 over. And that gives me here v3y 10 divided by 5.5. It gives me a negative velocity of 1.8 meter per second. So when piece 3 flies off in the southward direction, remember it's a top view question, in the southward direction at 1.8, it will have enough momentum to cancel the 10 from earlier. If you match it back up to the original picture here, so far combining the x and the y, what we've done, we had this bomb here, it fractured into one piece up, one piece down this way. We had already guessed it's going to be something down this way. We now have those two numbers. The Vx part has to be to the left, has to be westward, negative 1.9. These two values coincidentally happen to be very close together. That was just pure chance, okay, 1.9. The negative tells you it's actually westward, and then going southward, it has to be negative 1.8. Again, once you have the directions on, you can treat them as positive 1.9, positive 1.8. You'll do your plano Pythagoras. This would give you your total velocity. Velocity being a vector would give you a theta there. Okay. So two-dimensional problem, it's still conservation. It's still P in equals P out. And all we're going to do at the end here is just a little bit of Pythagoras. The hypotenuse is going to be the root. Notice I'm going to take this as positive numbers. I already have the directions in the picture. 1.9 squared plus 1.8 squared. If you can keep all your numbers in your calculator, even better. So the root of 1.9 squared plus 1.8 squared, I'm going to be off by a decimal or 2. The final speed that this piece has to leave with is 2.6 meter per second. That's only the magnitude, though, to give me the direction. I'm going to inverse tan, opposite over adjacent. Again, I'm just going to take the positive numbers because I already know the directions. Inverse tan, make sure you're in degree mode. 1.8 divided by 1.9 gives you a degree of 43 degrees. How would you call this angle here? We have our plano northeast, southwest. From the pure westerly direction, we end up aiming this many degrees south from it. So this would be south of west. So it is a little bit more work because we're separating x and y. We're having to do the question twice. And then whenever we need to, we just use Pythagoras and put it back together. Over the next two lessons, we're going to study vector addition again. We're even throw in impulse. So let's say that baseball analogy, instead of the baseball coming straight towards me, what if it comes to me as a parabola, as a nice arc for momentum to be conserved? Or if I supply an impulse, we're going to track what happens to the velocity there, as well as we're going to deal with a collision problem. Again, P in equals P out, except we need to do it twice with components. So I'm just going to leave you numbers so you can practice one more for a bomb style question. You're going to find in the first momentum package, the very last page has some two-dimensional setups. We won't be able to do all of them just yet until the next two lessons, but that's a good start for you to just practice. So I want you to just start off here. Again, we're going to deal with a top view problem. I'm just going to give you a few other numbers for a bomb style question. I'm going to give you the before look and the after look. This time what I'm going to do is I'm going to take this bomb, and this bomb here is actually going to be traveling to the right. All that's going to do is when you do your x, you're actually going to have some starting momentum. You're actually going to have a number that's not 0 here, but you still do the math operating on what the number is. So let's keep the math here fairly simple here. Let's say this is a 20 kilogram bomb. Let's say it's traveling 5 meters per second. So initially it already had a rightward momentum. Because it is a bomb, it's going to fracture again. I'm just going to do 3 pieces. It could have been 4, it could have been 5 and whatnot, but 3 seems good to me. This bomb here, as it sort of fractures, notice it already had a rightward momentum. As it fractures, I'm going to give you a few other numbers. Let's say we have a 6 kilogram object. This time it's going to be a little bit harder. I'm not going to give you that goes purely north. I'm going to actually tell you this 6 kilogram actually zooms off sort of diagonally this way. Let's give it a speed of 3 meters per second. And let's give it an angle of, I don't know, 40 degrees. Okay. Top view problems, that's going to be north of east. So that's one piece here. The other piece here, let's make it a, I don't know, 5 kilogram object. Let's get it to go at a more drastic angle. Let's get it to go at 2.5 meters per second. So this angle here, let's make it just 10 degrees. Okay. So the more tricky thing about this problem here, unlike the question that we did where it went pure north and pure east, where it was a little bit easier to say, oh, because I was, one of them is going to be 0. When I'm pure north, I'm not going left and right. When I'm going pure east, I'm not going up or down. In this case here, we do need to do our components. What I would do is I would actually find what's your v1x and what's your v2x. For this green one here, similarly find what is your v2. Sorry, let's call this. We're going to say object 1 is this first one. So v1x, v1y. This one here is going to be v2y, the downwards component, and then the v2x. So those parts there will actually enter your equation when you do the m times v. Those will just go in as components. You would have already had broken up components to actually get to the x and the y. So just careful of those two there. I'll leave you to figure out what this third mass is. Pretty easy, 20 minus the other two. Intuitively, based on these numbers, I still think this is going to kind of shoot off this way. But in this question, I haven't tried it out because I haven't done the numbers yet. But initially, you actually have a forward momentum already that might actually be big enough for this one to actually fly off, I don't know, maybe even this way or that way or this way, okay? So your job in trying to figure out this problem, I'm guessing that it should still be going this direction. I want you to find for me what is the velocity of this third piece. Find the final velocity of piece number 3. Okay. So we'll end our lesson there. If you have questions, just let me know. Thanks, guys. Take care.